I want to thank you for giving me the opportunity to share some thoughts in this very, very interesting session and effort to put some order in our thinking about inferences and p-values and what to do with them. I will try to present some empirical data about what have we not learned from millions of scientific papers with p-values. This is a map of the universe of science, just a latest snapshot of the last 16 years, trying to put some order in 20 million papers, 2 million patents that circulate in the literature. They form themselves into something like 200,000 different clusters. As Steve mentioned earlier, these clusters have very different ways of presenting their way of working with the scientific method, their data, they're making inferences and so forth. It's a little bit like thinking of a number of galaxies within the universe, and each one of them differing in terms of what is the number of solar systems, what type of chances are there that there might be life, what are the main elements that are bound, whether they're pulsars, whether they're dark holes, whether things disappear in dark holes. So the statistical inference tools that are used in these galaxies differ by tradition. Tradition is not necessarily justified. As Steve mentioned, people do that because other people do it. And p-values is the most dominant tradition within the larger universe of science nowadays. Null hypothesis significance testing is used by probably the largest sector in this universe, and there's clearly differences across these sectors. For example, in the biomedical and social sciences, a p-value of slightly less than 0.05 is enough to get you a paper, and a few of them are enough to probably get you a grant, and a few more of them are enough to get you promoted. In high energy physics, one is focusing on p-values of better than 5 sigma or 3 times 10 to the minus 7. And in genome-wide epidemiology, people want a p-value of less than 5 times 10 to the minus 8. But basically, all of these disciplines do use, in one way or another, p-values to try to make inferences. Along with David Chevalier and other colleagues at Stanford, we tried to take a broad view of the entire biomedical literature, try to see how many articles are using p-values and what kind of p-values are circulating out there. So this is an analysis using text mining of all items in Medline and PubMed from 1990 to 2015. This is about 16 million items, 13 million of them have an abstract, and within these abstracts, 1.6 million of them have also p-values. We also look at 844,000 papers in full text in PubMed Central. Of those, about half have an abstract, and again, many of those have p-values in their abstracts. What is the proportion of full text articles with p-values in their abstracts or in their texts? These are some proportions for different types of papers. And you can see that core clinical journals, about 80% of their papers have p-values, meta-analysis 83%, randomized trials 76%, clinical trials excluding RCTs 76%, reviews excluding meta-analysis, even those 22%, and all papers 51%. These estimates are underestimates, in fact, because we're not including p-values that may be tabulated in supplements, that may appear in tables, that may appear in figures. It's only p-values that spill over into the text and also in the or in the abstract. So people want to say something more than just using them to just tabulate some information. The proportion of PubMed items that have any p-values in the abstract is increasing. So this is happening pretty much in any type of design and any type of study and any type of journal. P-values are becoming a dominant epidemic across all biomedical fields on average, with some fields and some types of article being affected more than others. How small or how impressive are these p-values? This is looking at the number of occurrences between 1990 and 2015 for p-values in the abstracts. And you see that the vast majority of them are just plain vanilla p-values. They're not 10 to the x type of exponents where you would expect to see some very prominent, very low p-values with very extreme statistical significance. There's close to 5 million appearances of p-values that are on average slightly less than that magic 0.05 value, and actually a bit less than 0.01. And then you have only 20,000 that are 10 to the x, with an average minus log 10 p-value of 8.9, which is very close to the genome-wide significance threshold, in fact. This is looking at the distribution of the p-values in close to 400,000 full-text articles that have abstracts. There's different panels here, and they pertain to different types of studies and different types of journals. You can focus on the one that is at the bottom right, which is the entire PubMed Central, and you will see that then the number of p-values at or near 0.05 is larger than any other bin. If you look at the p-values in the abstracts of 88,000 PubMed Central papers that have p-values, then you can see that abstracts select more prominent p-values to report compared to the full-text articles. So if you focus again on the same bottom right panel, you will see that now the 0.05 bin is much lower in height compared to the first bin, which is the most significant p-values that are being reported. The next slide is showing these 4.7 million p-values in the abstracts of 1.6 Medline papers with p-values. Again, a similar pattern of distribution with heavy concentration at 0.05, but also more in the highly significant range. Let me introduce this R feature, which is the number of p-values at 0.05 divided by the number of p-values that are 0.001 or less. For the p-values in the full text of all PubMed Central articles, the R value is 1.11, which means that there is a bit more p-values right at the 0.05 bin compared to p-values at 0.001 or less. However, in the abstracts of the respective papers, the R becomes 0.59. It's about half compared to what we see in the full text, which means that more impressive p-values are far more prevalent in the abstracts than in the full text. How about different types of designs? If you look at meta-analysis, the R value is 0.47 in the full text, but it becomes 0.13 in the abstracts. If you look at randomized trials, there's still some gradient, but a bit less prominent, 0.68 going down to 0.49. For core clinical journals, there's a major drop from 0.84 to 0.27, so far more prominent selection of impressive statistically significant p-values in the abstracts of core clinical journals, and across all papers from 1.11 down to 0.59 in the abstracts. So there's multiple layers of selection in how we handle p-values in the literature. There's all the p-values that are obtained in the analysis that we do. There are the p-values that are selected for presentations in tables and figures. There's the p-values discussed in the text. There's the p-values selected for presentation in the abstract. And then there's the p-values that are used for making inferences and conclusions, maybe in the conclusion of the abstract, or being used one is making a talk, like the lecture that I'm giving now, which is probably trying to exaggerate the situation. How about tables and figures? I didn't show you any data on that. So here's some data that I have generated with Ioana Christea from our team at Metrics. This is looking at 3 high-profile journals, Nature, Science, and PNAS, and I'm showing you some data on corrected and uncorrected p-values. So on the left hand, you have no corrections. So this is just p-values with no Bonferroni or any other effort to correct. And figures and tables in these journals, both in 1997 and in 2017, almost ubiquitously report statistically significant p-values. So 98% of the p-values shown in figures and tables of these three journals without corrections are statistically significant using a 0.05 threshold. On the right hand, these are the results with any sort of correction, and the percentage drops a little bit. So it's 87%, but still it's pretty high. It's not 98%, but still the large majority of p-values shown in the figures and tables of these journals are statistically significant by nominal terms. The problem is that almost any result can be obtained, and anyone knows that in the presence of large databases, the analytical options are numerous. In observational research that has not been pre-specified, we have, for example, a very large number of choices to make on what to adjust for. So you can think of a regression model which is trying to estimate the risk of mortality for people in a population as a function of a candidate risk factor. And then there's many other candidate risk factors that may or may not be accounted for. For each one of them, we have two choices to include them in the model or not include them in the model. If you have 19 such factors, you have 2 to the 19 choices, which ends up being close to 1 million different analytical models that can be performed. And this is what I'm showing you here, which is the reason why we often get this wide vibration of effects and vibration of p-values and the Janus phenomenon. Janus was a Greek-Roman god. He could see in two opposite directions. And if you focus on the panels on the right, this is the association between vitamin E and mortality risk in the National Household Survey. It has a V shape for the relationship of the minus log 10 p-value on the vertical axis and the hazard ratio on the horizontal axis. And what that means is that 700,000 of this 1 million analysis suggest that alpha tocopherol or vitamin E decreases the risk of death, sometimes highly significantly so, and 300,000 out of the million analysis suggest that alpha tocopherol increases the risk of death, sometimes highly significantly so. So there is clearly some significance chasing bias that is going on across the universe of disciplines that use p-values. And significance chasing can happen in many different ways. One way to do it is through publication bias, which means that we have the typical file drawer effect. Negative results remain unpublished. The study gets completely hidden. It disappears. It goes nowhere. Nowadays, with all the competition and all the effort to get things published, it's not a very sensible choice to do a lot of work and not publish. So I think that publication bias tends to become less prominent compared to selective reporting bias, which means that negative results are manipulated or are reanalyzed or are creatively reanalyzed to become positive. Finally, there could be publication bias, which means that the data do not exist at all and someone is just faking positive results, but I think that this scenario is far less common compared to the other two. A very interesting approach to try to model some of that effort to get statistically significant results in the p-value universe is the work done by Yuri Simonson and his team on the p-curve. It offers a nice way to understand whether the distribution of p-values that we see reported is likely to come from p-hacking, so an effort to generate statistically significant results by manipulating the analysis to cross the boundary of whatever is considered to be statistically significant, or is related to genuine discoveries of real associations that are existing in the data. This is what one would expect. Right skewing is suggestive of the presence of true relationships rather than p-hacking under many simulations, not all of them, but under many circumstances you would expect to see that. There's a problem here, and the problem is that the p-curve analysis can operate well when we are dealing with experimental results with pretty much a perfection universe. If you think of much research being observational, extremely tiny bias can cause p-curves that falsely resemble genuine effects. And this is some simulations that we have run I've run it with Stefan Bruns from Kassel when he visited Stanford, modeling extremely small amounts of bias, maximum being less than what is considered to be a small effect, so 0.1 on a standardized scale, and many of these simulations use 1/10 of that. And even with 1/10 of half of a small effect being due to omitted variable bias, you would expect to see still some p-curves that falsely resemble genuine effects in an observational setting. Another approach is to try to model the publication selection process. So we can think of what different types of biases would cause on the shape of the distribution of p-values that we obtain. So if we have frank publication bias, then the center of the distribution of the z-scores would disappear, and this is how the new distribution would look like. And one could try to use different simulations about what the selection process might be. It could be a model that considers that initial publications have very strong publication bias and subsequent publications have less. Or it could be that we have what we call a Proteus phenomenon, which means that early studies need to find something that is statistically significant to be published. And in doing that, they tend to represent very extreme views of the evidence. But then once we have that, there's a window of opportunity for immediate refutations. So maybe within the next year or two, there's an opportunity for studies that are non-significant to appear. And after that early window, then we still have some publication bias or selective reporting bias operating that would drive the curve towards fewer non-significant results. We have tried to model different combinations of these factors and forces within large data sets. And this is looking at modeling done within large hypothesis testing genetics with different models. The best fitting model suggests that we see a combination of publication bias, of early extreme effects, and Proteus phenomenon. So we have to be careful because each field within these 200,000 clusters in the universe of science may have different sorts of selection models and different ways that p-values are cherished or not cherished and are sought or chased. This is a paper where we did some empirical evaluation of what is going on in a field which is very exciting and has lots of brilliant scientists working on, but nevertheless we make very little progress. Why don't we have treatments for most neurological conditions, even though we have hundreds and thousands of animal studies have statistically significant results? Well, the main explanation seems to be that these results tend to be an excess significant bias that is documented across this literature when we analyze thousands of these data sets of animal studies. We see that clearly there's more significant results than would be expected, even if the effects that are being described are true. This is a view of another field. This is nutritional epidemiology. And on the left panel, I have modeled with you real data from studies on associations between single nutrients and cancer. So these are standardized z-scores, and the green color is the effects and the respective p-values translated into z-scores from what is presented prominently in the papers. As you can see, there's a gap in the middle in the area of non-statistical significance. There's also a superimposed distribution with gray color, which is the effects and the respective p-values and z-scores that are in fine print. So if you read the paper very carefully, you realize, well, there's additional primary assessments, primary outcomes that were supposedly assessed, but they're not presented so prominently. So if you read the fine print, some of that central missing ground starts filling up, but still there's a huge gap in the middle. Most of the effects, based on what we know, represent effect sizes that are either completely null, or if they're true, they must be very small. So for example, fruits and vegetables, one serving of fruit per day will decrease the risk of cancer by about 1 in 1,000. So a hazard ratio 0.999. With the sample size that most of these studies have, one would expect the vast majority of the studies to have non-statistically significant results, but nevertheless, that middle ground is almost entirely missing. Meta-analysis may come to the rescue because if some of the studies presented extreme results in one direction and other studies presented extreme results in the other direction, maybe they will cancel out. And we do see some of that canceling, and some of the middle ground starts filling up, but it still doesn't solve the problem because it's not that the missingness is symmetric, and it's not that the chase for significance is equally powerful in both directions of statistical significance and both directions of effect. This is another illustration of things can go wrong with p-values. Problems with methods that have inherently inappropriate family-wise error rates. In that paper in PNAS about a year ago, the authors described how the use of some very popular methods for making spatial extent inferences with functional fMRI studies have tremendously inflated false positive rates. So a p-value of 0.04 actually would correspond to a real 0.8 or 0.9 based on the most popular parametric methods that are used in about 40,000 of these papers. It doesn't mean that all 40,000 papers are wrong. Probably a few of them are grossly affected and others less so, but clearly this is something that it took many years and it took many thousands of scientists and 40,000 papers before it was realized that that's the case. Another problem is emerging with the use of big data. Big data are particularly unsuitable to be attacked with p-values and related methods of inference. This is one attack on big data on the entire Swedish population. The Swedes have a wonderful national registry of all medications being prescribed, and they also have wonderful registry of all cancers being recorded in the country. So along with Chirag Patel, we tried to analyze all medications across the spectrum of medications prescribed as risk factors for the risk of cancer. And as you see, we got lots of p-values that are 10 to the minus 100. And 1/3 of known medications were found to affect cancer. This is clearly not believable. And actually, if you group medications into medication classes, then 3/4 of the medication classes may seem to affect cancer risk with very, very strong statistical inference. But clearly, this makes absolutely no sense. The problem here is that we have a lot of data, and we are applying null hypothesis significance testing in the presence of an extremely powered environment that is just creating havoc. Eventually, statistical significance has become a boring nuisance. Across the biomedical database of 15, 16 million papers, those that are p-values either in their abstracts or in their full text, 96% of them claim statistically significant results. The vast majority of them say also that they're novel, that they're wonderful discoveries. Is that believable? It's clearly not believable. 96% of the literature claiming statistically significant results. Actually, Dan Fanelli has suggested that fields with the highest proportion of statistically significant claims may actually be the least reliable. And you see a gradient here of statistical significance in favor of rejecting the null hypothesis for the primary pre-specified outcome, or quote-unquote pre-specified outcome, ranging from 60–70% in space science and geosciences and physical sciences, all the way up to 90% or more in clinical medicine, pharmacology, material science, and psychology, psychiatry. How about other ways of making inferences? How often are these used? This is looking at an in-depth assessment of 1,000 abstracts from random selection of the biomedical literature. If you focus on use of confidence intervals, abstracts with at least one confidence interval are just 1.8% of the total. Clearly, very, very low. Effect sizes, 11%, a bit less than p-values. There's a few more situations where effect sizes can be calculated, but clearly the dominant inference tool, even for making conclusions, which is very, very risky, is p-values. and not just p-values alone, but also qualitative statements about statistical significance. Effect sizes that are used can be anything. There's clearly not one best effect size, and I can live with any of those, but it seems that effect sizes are still not winning the war in terms of making a strong case that they need to be shown when results are presented and interpreted. So if you take 100 full-text articles from PubMed, this is how it's going to look like. 55 will report p-values, 4 will present confidence intervals for all the reported effect sizes, none will use Bayesian methods, and none will use false discovery rate methods. Of course, there are papers that use Bayesian methods, and of course, there are papers that use false discovery rate methods, but among 100 primary data articles, none of them is expected to use these methods, unfortunately, and report them. This has major connotations for the validity of the inferences that we make in most fields where p-values are used. Some fields where p-values have been used more successfully are those in clinical trials where, for example, Steve mentioned the 2 trials with p less than 0.05 FDA rule. I think it has worked relatively well, but even this one is not optimal. If you try to see what does it mean in terms of base factor terms, then it depends on what are the effect sizes that we're chasing. Most treatments in medicine are likely to have small effect sizes, so if the effect sizes are 0.2, then you run into situations where the rule of 2 trials with less than 0.05 can really be highly dysfunctional and can correspond to base factors that don't mean much and do not really increase much our belief into these data. If there's no effect, then obviously the situation can be totally miserable. So a month ago, I was one of the authors who joined this paper on redefining statistical significance. And I'm sure that among the 72 authors, there were 72 different opinions, but we all thought that we are drowning. We are drowning because of a flood of statistical significance, and we have to do something. And ideally, we need to change the entire world. We need to educate everyone. We need to make statistical education a sine qua non for every scientist, make everyone be a robust statistical thinker, and if not, at least make sure that they will use statistical help in every single piece of research that they do. This is going to take a very, very long time, obviously, and until then, we need a dam to contain the flood that is drowning us with statistical significance. So we said, let's add an extra 0, and this will mean that the base factor will change from something like 2.4 to 3.4 in most circumstances to something like 13.9 to 25.7, depending on how exactly you want to model the conversion of a p-value to a base factor. Is that going to save the day? It will be a temporizing measure because null hypothesis significance testing is probably unsuitable in most research applications. It is suitable in several of these clusters of the large universe that I showed you, but in the vast majority, large majority, I'm willing to take any of these 3 statements you may feel more comfortable with. It's probably not the best way to go. So, for example, these are some potential thoughts about whether null hypothesis significance testing is a good choice for. These are just some sorts of research that I'm engaged and many other in my field and in related disciplines work on. Is NAHT a good choice for developing a prognostic score for cardiovascular disease? Not really. Is it a good choice for assessing a diagnostic test for depression? No, nobody cares. Is it a good choice for evaluating a medical therapy in a randomized trial? As I showed you, it's not horrible, but it's not necessarily the best. Is it a good choice for mining electronic health records? No, completely miserable. A good choice for mining big data from metabolomics? Again, miserable. Is it good for, this is a circumscribed question that I was dealing with recently, for assessing if women athletes with natural testosterone should be excluded from the Olympics. A colleague of mine came with a paper that was showing highly statistically significant results for women who have high natural testosterone, and based on that paper, the women should be excluded because there was statistically significant difference But the Olympic Committee has decided that in order to be excluded, you have to have a specific competitive benefit of, let's say, 10%. What these data suggested actually was that a 10% competitive benefit was extremely unlikely. It would happen less than 1 in a quadrillion. I don't even know what to say. You know, less than 1,000 trillionths situations that competitive advantage would be there. So to conclude, as I'm approaching midnight, the use of p-values has become an epidemic affecting the majority of scientific disciplines. Strong selection biases make almost everything seem statistically significant. Null hypothesis significance testing and p-values are inherently most suitable, optimal for only a minority of current research. Using a more stringent threshold is a temporizing measure to avoid death by significance. Null hypothesis significance testing and p-values may be replaced in many fields by other inferential methods, and selection biases will need more drastic measures to be curtailed rather than just a change in inferential method. I will close with special thanks to a number of my colleagues who have contributed to some of the data that I showed you today, and hopefully there is still some time for questions. Thank you.
Thank you.